Okay, so I wanted to give you guys a little bit of a background on respiratory lab. You should have listened to the respiratory lecture first. If you haven't, you should go back and listen to that. Study that for a little bit and then come back and see if you can do this. The first thing that you're going to figure out is a chemoreceptor reflex. Let's go over this. So your mechanism to breathe is based off of CO2 levels. So CO2 levels increase, right? When you increase CO2, right, when you increase CO2, what happens to production of carbonic acid? Okay, so remember your equation, it's CO2 plus water, right? If you have more CO2, that's going to drive the reaction forward. You're going to make carbonic acid. Um, and that is going to acidify tissues, right? So if you keep going with this, you're going to increase protons, right? And you're going to make bicarbonate. You'll find out typically in the tissues, any increase in CO2 is going to make acid. So you're going to have excess acid, okay? So if you think about it, you're going to have increase in protons, and that is going to cause a drop in pH, right? So it's going to be acidic. So anytime your mechanism to breathe is based off of CO2, and as CO2 goes up, you have an increase in H plus and your pH drops. It becomes more acidic. What senses this? Your sensor, you have two of them. You have peripheral chemoreceptors in your aortic arch, so coming off your heart, and carotid sinus going up to your brain, and then central chemoreceptors in your medulla oblongata. When I see receptors, a lot of receptors, this tells me that this is a really sensitive system. To go with that, you know that pH of blood needs to be 7.35 to 7.45, right? When you increase the protons and you drop the pH, you're going to start creeping on this area. When you start decreasing pH, these guys are going to get sensitive to it, or they are always sensitive to it, and so they're going to send that impulse. They're going to start firing faster and faster and faster to that medulla oblongata. And the medulla oblongata is going to get those increase in impulses and say, oh, CO2 is getting too high. We need to take a breath. And so it's going to send a signal out to your diaphragm and your external intercostals to tell you to take a breath. There's also your scalenes, your sternocleidomastoid, and you don't have to know all the other ones. Accessory muscles, these guys are fine. Note that this is inhalation, right? Be careful because internal intercostals deal with forced exhalation, okay? These guys are for inhalation. What do these guys do? They're going to increase the depth of breathing and the rate of breathing, all right? So that CO2 ultimately drops. So CO2 increases, this triggers you to take a breath, right? CO2 increases, this triggers you to take a breath. You can play with CO2 levels in your blood. So CO2 levels usually are around 40 to 45 millimeters of mercury, okay, for CO2. Okay, that's the range for CO2. For oxygen, it's different. It's about 40 to 100 millimeters of mercury of O2. And so because this is such a narrow window for CO2, this tells me that this is highly regulated along with pH. So when CO2 starts hitting the 45, those CO2 receptors, those chemoreceptors are going to start firing to the medulla oblongata, and that's going to cause you to take a breath. So CO2 builds, you take a breath, it drops. CO2 builds, you take a breath, it drops. That's your primary mechanism to breathe. Secondary to that is oxygen levels. If oxygen is really low, like if you're at Big Bear or Mammoth or whatnot, where there's less oxygen, then that's going to cause increase in ventilation on its own. Okay, but typically in a normal healthy individual, we don't worry about that. Okay, so you're playing with this. So if you're hyperventilating, if you're breathing deep in fast, you're going to blow off more CO2 than you need. So it's going to take you longer to hit this number, right? If you hold your breath, like if you rebreathe CO2, and if you're breathing into a paper bag, then you're going to hit this number faster, right? So you're playing with that. Then we're going to do a slow vital capacity. The slow vital capacity for lab looks a little bit different than the one that I'm going to go over with you, but you should be able to apply it to any slow vital capacity. So tidal volume is the amount of air you move in a single breath. So take a breath in, let it out. That's your tidal volume, okay? Inspiratory reserve volume is the amount of air you can forcefully take in above tidal volume. So take a breath in. That was your tidal volume. Take more breath in. That's your inspiratory reserve, okay? Expiratory reserve is the amount of air you can exhale past normal. So inhale, exhale normally, exhale past that, okay? That's your expiratory reserve. Residual volume is the air that's trapped. Your vital capacity is the maximum amount of air moved through the lungs. So it's tidal volume, IRV, and ERV. Here's a plot of slow vital capacity. Why is it called slow vital capacity? Because you were breathing slowly when you did it. So it's a normal breath. Like if we were doing this in lab, it'd be a normal breath in, out, normal breath in, out, maximum breath in, and maximum breath out. Okay, and release it. So tidal volume. Pay attention to the scale. So is this in mils or is this in liters? Okay, this is usually, let's see, residual volume. We'll say, let's say this is, I don't know, 1, 2, 3. That looks a little bit off. So let's do 3. So let's do, this would be 0, right? Whoops. This would be, I'm going to put 1 liter here, 2 liters, right? Then let's do, I don't know, 3 liters and 4 liters, okay? On your spirometry data, it'll be labeled for you, so pay attention to what these units are. How do you figure out what your tidal volume is? You're going to take the smallest waveform of the two, right, and extrapolate over. So this is supposed to be, it's supposed to be 500 mils, but it looks a little bit less than that based off of my labelings. But we'll just say it's 500, okay? So this would be 2.5, and this would be 2.0, right? So then your tidal volume is 2.5 minus 2.0, right? And so that gives us 500. That's your tidal volume. It's your peak minus your trough. Expiratory reserve, which one is that? So expiratory reserve is the bottom of this waveform minus the bottom of your expiratory reserve. So it would be 2 liters minus 1 liter, which would give you 1 liter, right? What's your inspiratory reserve? It would be 4 minus 2.5, because it's the peak minus the peak of your tidal volume, which was 2.5. So that would be 1.5 liters, okay? And then vital capacity, add them all up. Residual volume, you need to calculate that. Okay, so this is slow vital capacity. Forced vital capacity is a little bit different. So it's still measuring vital capacity. So this should still be the same predicted vital capacity, right? Let's back up a second. So this vital capacity is, let's say, 1.5 plus 0.5 plus 1. So that gives us 3, okay? And this is really low, that's fine. So that gives us 3 liters. So that should be the same as this. This is the peak of your, what you blew out is your max, and that they should be the same theoretically. They're not usually, but they should be the same. How do we do this? You take a deep breath in and force it all out in 3 seconds, okay? What are we interested in? We're interested in how much air you blew out in 1 second, which is forced expiratory volume at 1 second, right? Because this is at 1 second, versus your forced vital capacity, right? And we're interested in this compared to predicted, okay? So I want you to make your measurements, right? So this would be your FEV1, and then your maximum value, and go through your lab and do that. But what you're interested in is you're going to take that FEV1 divided by your FVC, right, which is your forced vital capacity, which is your maximum. So this is how much air you blew out in 1 second. This is how much air you maximally blew out, and times it by 100 to get it in percent. It should be greater than 80%. Okay, so what that's telling you is you should be able to blow out 80% of max in 1 second, okay? If you can't, that's telling me that your bronchioles are obstructing airflow, okay? And it's in the next slide. So your bronchioles are obstructing airflow, right? We're also interested, so that's, so this is gonna tell you, this is a test to tell if you have an obstruction. Whoops. Okay. The next way that we use this test is you want to look at your actual forced vital capacity, what you blew out or what your volunteer blew out, and it should be greater than your predicted. Where do we get the predicted forced vital capacity? From the machine. So you put in your gender, age, weight, height, ethnicity, and it gives you predicted, okay? Your actual, what you blew out maximally, should always be higher than or equal to predicted for you. If this is less than predicted, that shows evidence of a restriction. What is a restriction? It means there's damage to that lung lining, and so the lungs can't inflate. You can't get as deep of a breath, right? Your lungs can't inflate like they would, okay, because you have scar tissue. So example, COVID-19 patients, they have trauma to their lung lining, and so they are going to have a pulmonary restriction, obviously while they're going through the disease, but once the virus has damaged the lung lining, they may be stuck with respiratory issues for the rest of their lives. Same thing with pneumonia, same thing with tuberculosis, same thing with emphysema and chronic obstructive pulmonary disease. Chronic obstructive pulmonary disease is called that because it's an obstruction, but as you damage that lung lining from cigarette smoke or from asbestos or whatever, it's going to encroach upon this, right? So obstruction is obstruction in the trachea and bronchi, right? That these guys are constricted, so they're not letting air flow through the trachea and bronchi. Okay, I use a boba straw compared to a McDonald's coffee straw, right? You take a deep breath in, you blow through a boba straw, really easy to do. You take a deep breath in, you blow through a McDonald's coffee straw. That takes forever to do, okay? You can't get out 80% in 1 second, and so that's an obstruction. Okay, so I want you to go through the lab, and you can look at this stuff if you want to. Go ahead and read through it. It's really interesting. It covers some of the stuff in a little bit more depth, but I want you to go through the lab. Oh, there is one more thing. So for this one, the slow vital capacity, the waveforms that I have, be careful, because I think inspiratory and expiratory are flipped, okay? So be careful. Normally, this is your tidal volume, inhaling, exhaling, right? But with some waveforms, they do it differently. So this is inhaling, that's exhaling, inhaling, inhaling, and exhaling. Okay, so it's flipped, so be careful. Same thing with vital capacity, forced vital capacity. Normally you see it like this, but you can also see it like this. You can see it flipped. So you guys should be able to apply it regardless. Okay, email me with questions.